Okay, so this is a review of the FIR filter design. Okay, just a moment. Let's just first try to. Something like that. Okay, so the FIR filter design, and especially the windowing method, since that's the most, well, that's the simplest one to understand. And everything actually starts from a continuous time system parameterization. So if we want to have a system, this is the continuous frequency space, a low pass filter with cutoff frequency at omega c, that's the negative frequency range. Just to make it physical. Okay, so it basically just means that it doesn't, the behavior of that filter does not change for different phase signals. That's what it is all about. Okay. Anyhow, so we start from this kind of window in continuous frequency space, and then we know if we do a Fourier transform of that one, we will get it actually, or actually inverse Fourier transform. We get a the system impulse response, and for that sort of thing we will get a sinc form impulse response, and this is now continuous time impulse response. Next we will basically make this a sample system by, well, simply sampling the impulse response. And so, and we make it finite impulse response by multiplying with window. Okay. And in this case, if we multiply this one with the square-shaped window, so that does actually the same way we were producing this square-shaped signal on the second exercise, on the fundamental signal. So what is actually first exercise? Same way, basically mathematically, the only way to cut this impulse response as a finite impulse response is to multiply it with the with that square-shaped window or something that else. So now the h of n is actually, well, that's the sinc of something. That's sinc of something. And then our FIR system coefficients are simply that window times the sinc, and there's a constant also there. Okay. If we then do the analysis of this system back to frequency space by doing the Fourier transform of the window sinc, we will actually end up having this part Well, the sink still has the Fourier transformation of inverse Fourier transformation of this one is still a box. So it's perfect that sense. But in addition to that, there's also the this box in time space, which transforms into sink in frequency space. And the basically the Fourier transformation has a kind of funny feature that if you have a multiplication in one end, when you do the transformation, you get the basically convolution on the other. The same way as all these filters are working, we are doing actually convolution between the this signal and the impulse response, and the signal is actually the output when you convolute it. But basically the same way, if you have multiplication in here, it's actually convolution in here. So you will get some edge effects here. So basically, and the absolute value. And of course, this is only valid between Nyquist frequency to plus Nyquist frequency. Okay. So that means when you are doing this boxing on time space, you are at the same time you are producing some non-zero attenuation or non-zero pass bands on the stop band region. Okay. So this is supposed to be no pass here. It's a stop band. But due to this windowing, actually you have some, say, some non-infinite attenuation due to the box form or box shape. Okay. And then, if you want to have a better stop band attenuation, you need to reduce the amount of high spectral components on the box, meaning you need to get rid of this sharp transition. For example, well, if your original stop band attenuation would be here for sharp box, if you smooth the box somehow nicely like that, then you actually have more stop band attenuation. At the same time as you basically also lose some of the transition bandwidth. So the transition bandwidth goes higher, while the stop band goes better. Okay. Then another property of the say sample systems, you can always take a wider sample, wider window. Oops. By taking a longer time sample here, you take more points. Basically, that one would reduce the this transition bandwidth. All right. So basically, we have 3 parameters here that we can fix in order to get the filter properties as required. The first, so design. Of course, you must have the cutoff frequency somewhere. But that's simple since that goes inside of the sink. I think it was FC divided by Fn, sink n times Fc or Fn, where Fn is the Nyquist frequency, sampling rate divided by 2. Okay? So that's the first parameter. So where is the cutoff frequency? Okay, the second parameter is basically how much do you need the stop band attenuation. Stop band attenuation. And that's basically comes from the width, the shape of the filter, shape of the window. Okay. Third parameter, how to fix the rest of that stuff actually is the width of the window, which affects on the transition bandwidth. Yes?
What do you mean by shape of the window?
How smooth it is.
Okay.
Yeah. Shape. Smooth. Has less power on high frequency components.
How would you define that in MATLAB?
I'll show you. On high frequencies compared to lower frequencies. Okay. Then the transition bandwidth. That actually comes from the width of the window, meaning how many points you would take in on either side of the on this sink. Okay. I'm using here symmetric sink because I want a linear phase response. When you make this one symmetric, then you are actually having a linear phase response. Okay, so those are the design parameters. And just to remind you about the filter properties overall, if we have a low pass filter, it has a cutoff frequency. Then it has actually stop band start frequency. And the cutoff frequency is usually either minus 3 dB point or some other dB point, x dB point of the filter. It depends actually on the ripple of the filter or the let's see, ripple, or if it doesn't have any ripple, then it's minus 3 dB. Okay. Anyhow, then that's stop and start frequency, meaning basically that. Oops. Let's make this kind of box here. So that defines that point. Then we have cutoff frequency. Then we have basically the required attenuation level. A. And basically the filter should go something like that. So after that stop and start frequency, all the filter should attenuate the signal at least at the certain rate. Okay, so those are the basically design parameters for any low-pass filter. And that's the pass band. That's stop band. So this is transition band. Okay, the naming conventions. Okay. Then we also have some filters actually have some ripple, if any. Meaning, if a filter has ripple, it basically behaves something like this on the pass band, and then starts going down. Okay. So let's take a quick look on the MATLAB how to design a simple window system. I do it by copying and pasting. All right. So. Alrighty then let's see, I had the template somewhere. If I feel the MATLAB command is by the way, there was a wrong link on this one last week, so I fixed it on the 14th, was Thursday. Okay, wow. Let me first take these 4 comments. Okay, 4 first comments. So 11 point, okay. 11 point running average versus 111 point running average, just to make a notice. Okay, so fundamentally what I have here is the effect on this figure 2. Sorry. Fundamentally, this is the effect on how the width of the window affects. So currently I don't have any sync on my the impulse response. I have just this impulse response of a running average, which is just this square box, which transforms into the sync. And actually that is the absolute value of the sync and in logarithmic scale. Okay. And if we are looking at this definition of how these filter parameters are actually defined, we can quickly see that this running average filter is not that great, since it has only about, actually it has only about 13 decibels of attenuation on this stop band. Okay, and if we are doing basically the wider so add more values to your running average. What happens if you are basically comparing it to this picture? There, we still have the same amount of attenuation on the stop band. It doesn't affect on that one, since this, by adding more values to your running average, you are just basically squeezing the spectrum on the spectral space. So, you know, multiplication of time, meaning you are just dividing the frequency. It still has that attenuation is very moderate for that long filter. Okay. Let's take another picture then. Design with sampled sync. All right. Up to here. So 2 kilohertz sampling rate. Frequency the cutoff frequency 100 hertz. 11 points. And well, that's Nyquist frequency, so it should be Nyquist frequency. And then the sync, and then the stem, where is the stem? Okay. Okay, so what I did basically was just took the let's see, what did I do? Oh, this is this sampled sync and cut it into basically that part of it only. And what I should have here on my left hand side, the frequency response, where the 3 dB point is actually at 100 hertz. Let's see. Yeah, more or less. It starts at -1, so that's about -3 dB point. So yes, the cutoff frequency actually can be handled by putting the cutoff, a design cutoff frequency into the sync. That one. And let's take more points. There. Okay. So this is, in principle, this is about the same as, wait a minute. But as this, except that we have the cutoff frequency. So on the right hand side there's the 111 point running average filter. On left hand side we have the 111 point sampled sync with the cutoff frequency at 100 hertz. So it seems that yes, this FC actually, when you put it on inside of the sync, actually it controls the cutoff frequency quite nicely. Now the next problem here is the it still inherits the stop band attenuation, the parameters or the functionality from the sync part. Okay, or the box part, yes, with this sync on frequency base. So next we try to do some other windowing, and yes, there are some windows. I will start with my favorite, which is Hamming window. All right, so that's still this basically this 11 point to make the point. So left hand side I have the original 11 point sync with the correct cutoff frequency, but just square shaped window. On the right hand side I have the Hamming type window, which basically reduces the amount of, let's see, can I add some line here? Box. Okay. No. Where's that goes on rotate. Well, whatever. Anyways, on left hand side, let me put this on the same scale. About 80 dB right there. So on left hand side, on the original, we have about 18 dB attenuation right here. On right hand side we actually have 45 decibels of attenuation, meaning much more attenuation on the stop band. But on the left hand side we have wider bandwidth. No. On the right hand side we have wider transition bandwidth. Okay. So if we want a sharper filter, we need to now take more points. Since okay, shape affects only on the affects only on the stop band attenuation, and the cost there is basically that we are widening the transition bandwidth. And finally, basically, on the third point we choose the transition bandwidth such that we can fix this inside of that box. So basically, we started from here and now we just move this one. So squeeze the transition bandwidth by multiplying the time, meaning taking more points. Let's see what happens here. Boom! It looks like I have something funny going on here. Let's see. Where's my sync? Where's my sync? I miss my sync here. Oh, there. Oh. That's what happens when I'm trying to make a point here. But anyways, so let's see. Maybe it works like that. What? Oh, I see. Of course it doesn't work. Why do it? Let's try it from the beginning. Okay, there we go. SSW2, it's not here. There. So that will be the final answer. So fundamentally, when you fix the cutoff frequency, shape of the window, and width of the window, you will get the exactly the parameters what you want from the filter. So this one has a 100 Hertz cutoff frequency, 50 Hertz transition bandwidth, and then basically it has about 50 some Hertz, 50 some decibels of attenuation on stop band. Okay, so that's the first half of this the history file. So where to find the different kind of the windows then? Basically, well, if you take a look at for example that Hamming window documentation.
Can I ask a small question?
Yes.
That cutoff frequency,
Yes.
is it minus 6 dB or minus 3 dB?
It depends.
Yeah.
In digital filters, it's minus 3 dB or the amount of ripple.
I was just checking that
Yeah. Yes.
goes down so fast in the
Yeah.
plot there.
So it's generally speaking, it should be basically the amount of ripple defines the cutoff frequency. But if it doesn't have any ripple, then it's minus 3 dB point. Half the power. Yeah. Okay. So, and for example, on Hamming window, you can see also Blackman and other windows, including also the Win tool. You can define your own window. It does not actually have a link to the Kaiser window, which is actually a tool to generate all kinds of windows. But anyways, the world is full of windows. You just pick whatever you want to follow or watch out. Basically, one way to do the exercise, since there's the stop band attenuation requirement, take a look at those window spectra. So this window, for example, has the, let's see, it's 30 dB to minus 10, so it has about minus 40 dB the attenuation. Okay. If we are taking a look at some other windows of Han, this is one Han window, so it has a little bit more, I think. It depends how you where do you start it. And basically, it's a good idea to, when you're comparing different windows, also include the cutoff frequency. Since if you don't include the cutoff frequency, then basically it's hard to. It's much easier to check it from this picture overall. Okay, good. So that's where you find the windows, and I think I also had a. Did I have a table? Table, sampling, convolution theory. Okay, yeah. There's also table which shows the stop band attenuation on this one. Okay. Good. And now we have a FIR low pass filter. How to transform this one to band pass filter. That actually is the idea of modulation. Modulation is actually the same as you would convolute in spectral space. So convolution in spectral space to transfer actually this low pass filter properties into some other frequency. Like base one. So we have a low pass filter here. Remember, it's almost always symmetric. So there are these negative frequencies. There's some symmetry. Okay. And actually, if you take this and convolute it with this spectrum, you would get transform those properties into new planes. Okay. And convolution in frequency space is same as multiplication in time. Okay. It's always there's only one rule to remember. If you convolute, if you multiply something on one space, when you do the inverse space, then it's the convolution, and vice versa. All right, so if we have modulation frequency of FM here, and we have this nice window sync function here, you need to just multiply this one with either cosine or sine. Sine is usually not a good idea, since you can end up with a lot of zeros with that one, and then you start basically messing up with the frequency response. So there's a danger when you are using sine to multiply. At least it will be 0 here at the origin. So cosine 2 pi n and then the modulation frequency divided by sampling rate times something. Actually, that times something means that when you are basically doing the convolution, never forget the left-hand side. Half of the power will be there. So you need to multiply this one amplitude by square root of 2, I think. All right, so back to the business. So convolution, history. Transient bandwidth, low pass. Where do I have the low pass? Transition. Low pass to band pass filter transformation. So we modulate with center frequency. So for example, here I have center frequency of 200 Hertz. Okay, let's take those first. Whoops. What did I do here? Center frequency. Okay, and then maybe it's that. Oh, I see. I just had an error on my. There. Okay. And then the. Oops. That one. There. Oh. Yeah. I'm scaled, modulated. the low pass filter at 400 Hertz. So original was this one, I think. Yeah, so that's the low pass filter where I started from, and then I have the just the only thing is here is that I modulated it 400 Hertz sample cosine wave, and now I have a band pass filter with the same properties as on the low pass filter, except, okay, this is a common source of mistakes. See, this cutoff frequency here actually defines the half width of this filter. So basically, if you need a filter, for example, with the 200 Hertz bandwidth, you start with 100 Hertz cutoff frequency on the on low pass filter. Okay. Then the special case, how to basically transform low pass filter into high pass one. So nothing funny about it. This modulation frequency is then just this Nyquist frequency, and that's it. Then you don't need to multiply it with any scaling factor there. Okay. Low pass to high pass. Here I have it. Wow. There I have the high pass filter. But okay, another warning. The bandwidth or the cutoff frequency here defines the bandwidth of the high pass filter. Okay. I'm asking on the exercise the real cutoff frequency of this high pass filter. I'm actually telling you, giving you this one, not that one. So, what kind of low pass filter you need to design then? Actually, think of the
What do you mean
result.
by the real cutoff? What do you mean by the real cutoff frequency? Is it not the same that is
Yes,
there?
it's a cutoff frequency. Cutoff frequency always measured from the zero. Bandwidth is here. So
Yeah, it's cutoff frequency.
it's cutoff frequency.
Okay.
If I'm giving cutoff frequency, basically you need to measure that value here to use it as the design for the low pass filter. Okay. Just that's how you do it. All right. So an example. Oh wow! I have new high pass filter. What I'm doing here? Let's see. Okay. Yeah. So basically, whatever your low pass filter is, you just basically when you're doing the modulating with the plus minus ones, basically, it basically takes the real axis on the z plane and reverse the order. Okay, so that's another example. And then the band stop. Band stop is simply band pass. Whoops. Where do I have the HSW2? What happened to my? Where is this HSW2?
Second line is an error.
Oh, this second line. Yes, this one has an error, right? Ah, yeah, I see. Alright, so that was the error. I usually clean these files, but it seems that I have been lazy. Okay, so that's basically I took the oops. Doo-doo. That was this high pass filter and the original low pass filter. Was this one? No. Low pass filter. Must be that one. Yep. So basically what I did, I just took these two one low pass filter plus the high pass filter. As long as those impulse responses are the same length, I can add them easily. And when you add the impulse responses, you basically just add the properties, and well, because of the linearity of the system, okay, you can add them, and that's the result. Just one small reminder about the stop band attenuation. You are adding those stop band, how much do you pass the signal on the stop band on both ones. So fundamentally you're rising that that level at 3 dB. It's at 3 dB higher. Not much more than that, but anyways, you get a little bit of loose on the attenuation, but anyways, it's still a decent stop band filter, wide stop band filter. Okay, so basically these are the tricks to do when you are doing the FIR exercise. I let you work on the exercise for the next 1 hour, and then at 1 o'clock I start with the IIR. Okay, good. Any questions? No? Okay.